Well, yeah, of course. It's interesting. Like sport, like I feel like this is something I struggle with, like to get across to people. Is like two things can be true. One is like competition's supposed to be fierce, so like it should get chippy and it should get a little lippy and it should get a little right. Like that is part of the game. But then, no, they don't. You guys just all take it so personally. Because then the other thing to know is that when the game is over, the game is over and you can be friends, right? Like that's how it works. You get intense, you get chippy, and don't be wrong, you can hold a grudge, but don't be a baby about it. You know, it's part of the game. Anyway, all right, let's get to it. Shh, shut up. Shut up. Okay, first things first, we're actually going to not do equilibrium. We're just going to, quiet. We're going to remind ourselves how acids work. Which, if you recall, strong acids go to completion. They do not form equilibria. So that means for any one of these, there's no equilibrium. But we're going to do a question here, and in so doing, we're going to remind ourselves how acids work, and we're going to give ourselves a slightly new definition of acids. We're going to describe what we call the Bronsted-Lowry theory of acids and bases.
Is that the theory that came after Arrhenius theory?
Yeah, look at you. It's an O with a slash through it. It's a Nordic thing.
Is it Lowry or
Lowry. Okay, so the basic idea is this. Acids are proton H plus donors, and bases are proton H plus receptors. All right? Receptors? Lowry. It's a name. Settle down. Okay? So, and they must exist in pairs, because if something gives up a proton, then something else must accept it. Does that make sense? So, for example, our nitric acid. Which one of these is nitric acid? HNO3. Okay. So, in this example, we have HNO3. That is our acid. Does that make sense? What's going to be the base that accepts its proton? Well, we say that an acid becomes an acid when we dissolve it in water. So the base in this case is actually going to be water. This is the new theory, where it's just a different way of thinking about it. And this one, like we said, isn't in equilibrium. It's just going to go to completion. But we're going to say that the acid is going to give up its H+. When HNO3 gives up its H+, what will it then be? NO3. And it'll have a charge of -1. And then if the water takes the H+, we've only just said the H+ is dissolved in water. But the truth is not just dissolved in water. It actually is going to stick to the water, because the water we know is polar, and it has a slightly negative side. And so the plus is going to stick to that. So what will you end up with? H2O is going to become H. You could say H2OH if you wanted, but nobody does. We just say H3O plus. And these are all dissolved in water. Except for this, which is, I guess, not dissolved in water. It just is water. Does that make sense? So everything's dissolved in water except for the water, which is just water. Okay. Cool. So, there we go. Now, that's all well and good, right? It's all well and good. But it asks us to find the pH of a beaker that contains 25 mils of 1.4 mole per liter nitric acid. Does anyone remember how we calculate pH? What's pH?
Concentration of H.
Yeah, it's a mathematical operation. Do we remember this? pH is equal to the negative log of the concentration of, we used to always say H plus. Now we're going to use a slightly different definition. We're going to define it as the negative log of the concentration of H3O plus.
So you put the base in there? No, just the water.
Because we're going to introduce some terminology here. Not yet, though, actually. We're going to do it when we get to equilibrium. This is not the equilibrium one yet. So, in this case, this question is trivial. What's the pH? It's the negative log of what is the concentration here if all of our HNO3 is going to become NO3 minus and H3O plus. What's the concentration then? Concentration of H3O plus, this one's easy. We already know it. No math needed. What's the concentration?
0. 1.
Which one of these is a concentration, team?
1.40.
Good. 1.40 moles per liter. Good. Very good.
I didn't see that.
So the negative log of, what's the concentration here? 1.40. Because it's a strong acid, all of the acid,
Wait, I'm kind of confused why you put H3O plus instead of just H plus.
this is our new definition of an acid, which is an acid now no longer releases an H plus ion. It does, but it doesn't just release it. That H plus ion has to go somewhere. And we're saying now we're going to have a slightly more sophisticated understanding that actually we don't just have free H plus ions floating around. We actually have H3O plus ions floating around. Because
So it's just like explaining which one's a new acid coming from water.
yeah,
Okay.
yes.
You're lying to us the whole time.
Nope, it's just a different understanding.
Withholding information.
Sure.
So it means that water can act as a base and acid, right?
Yeah, we'll get there. See, look at you. Look at you, clever kid. So this is a strong acid, therefore all 1.4 molar becomes H3O plus. That doesn't look like becomes, it looks like I had a aneurysm while writing it.
Then where did the NO3 go? They would
Still in there. The NO3 minus is floating around. Like that. And let's do this math. What is the negative log of 1.40? I think you know I'd like that answer to the appropriate number of significant digits, please.
0.146.
Whoa. Okay. Sarah, I was listening to you. Give it to me again. Negative.
0.1461.
How many sig figs?
3.
So 0.146. Okay. Therefore, shh, guys, focus in. So the pH of 1.4 molar HNO3 is negative 0.146. Does that feel okay? Yeah.
How are we able to find it without knowing the math? All we needed math was pH, and not just concentration.
How do you calculate pH? pH is power hydrogen. The definition of it, it is the negative log of the concentration of H plus ions. In this case, we're going to call them H3O plus ions because that H sticks to water. So all you need to know is the concentration of H3O plus. Do I know that? Don't worry, Kartik. I'm going to give you plenty of hard questions. All right? Lots of hard ones to come. More than you want, I'm sure. All right? This one, easy. I asked you to take the negative log of the concentration of H3O+. This is a strong acid, so all of the acid is going to turn to H3O+. So the concentration is what? So what would you possibly do with a mass? I mean, you could convert that to a mass if you wanted, and then convert it back to a concentration. But what you would end up with is 1.40. Does that make sense? Like, you could do all that, but you'd just be doing work for no work. Like, it's been done for you. Does that make sense? Cool. Don't worry, Kartik. Do you want my word? I'm gonna give you some hard ones. Don't worry. All right. That was a nice fastball across the plate. I'll give you some curveballs. Don't worry. All right. I got a knuckleball waiting for you. All right. So listen. Look here. Here's our new definition of an acid. An acid is something that has a hydrogen ion available to donate that reacts with some base. We are going to say in the presence of water, most acids form equilibria. Other than the list above, any other acid is going to form an equilibrium. And on the other side will be the acid now stripped of its hydrogen and that H3O plus ion. Now, there's one thing to consider here. Ready? This is the acid. And this is the base. Because when this reaction goes in the forward direction, the HA gives its hydrogen to the water. The thing that gives away the hydrogen, well, that's an acid. The thing that takes the hydrogen, that is a... Okay, now look at me. The reaction also goes in reverse. When it goes in reverse, what's this reaction? A minus bumps into an H3O plus and turns into HA and water. Pause. Does that make sense? Don't worry about just okay. So don't write this. Look at me. Put your pencils down. Pencils down. The reverse reaction looks like this. H3O plus bumps into A minus and it forms what again? HA and okay, do not write this. Leave those pencils down. If this were the reaction, which one would we call the acid? What would we call the A minus? The base. So, in the reverse reaction, the species that had been the acid is now what we call the conjugate base. And conjugate just means on the other side, or paired with. Yeah, this you can write down. So on the other side, the language isn't all that important, but it gets, the language is just language you're going to hear a lot, so you've got to be used to it. In the reverse reaction, it is the H3O plus that gives away the hydrogen. That makes it the conjugate acid. All right? We need to be comfortable with that. Does that make sense? Now, if we were to write a KEQ statement for this, bless you, what would we get? Yeah. Let's do this first, then I'll then ask you a question. If we were going to write a KEQ statement for this, what would we get? Concentration of A minus. Yeah. Yeah. Very good. All right. Yeah.
How do you know which ones to put on the top or bottom? Because
What do we always put on the top?
That is so wrong.
That's okay. You caught yourself immediately. What do we always put on the top? Yeah, we always put the products on top. We always put reactants on the bottom. That's a convention. No, that was wonderful, and it was such a beautiful woo. That was like, I wish if I could make that sound, I would make it all day long. It sounds so lovely. It was very charming. Anyway, all right. So now, one thing to note: The concentration of water in water is a real thing. There actually is a value. Believe it or not, you can do the math. You can figure out how many moles of water are in a liter of water. The nice thing is this, is it doesn't change. So it does actually have a value, but it is a constant value. So rather than constantly calculating that and shoving it in there, since it's constant, what could we do with it? We could fold it into the constant. We could fold it into K. Does that make sense? We can just do it on the other side. We can say, okay, KEQ is now divided by the concentration of water, and we're not going to write that every time. We're just going to give it a new name.
Divided and multiplied.
Oh, sorry, multiplied. Whoops. Concentration of water times KEQ. But we're not going to write that every time. Yeah. I do not mind moving a bit that way. How's that? Good. And since we're just doing that, we'll just give it a new name. We'll say it's a new constant, and we're going to call it Ka. A for acid. Or apple, if that's helpful to you. And that would equal the concentration of A minus times concentration of H3O plus. In other words, the concentration of the conjugate base times the concentration of that H3O plus ion divided by the concentration of HA. Yes.
For H3O,
Yep.
if you had more, like, had a bunch of different acids in a container, would it be H5O?
No, that's a great question. Nope, each water can only take on one hydrogen ion. So it'd still be H3O plus, you just have more of it.
Oh, so, okay.
Because there's lots of water. There's functionally infinitely more water than anything else. When you dissolve something in water, there's a lot more water than there is stuff you're dissolving. So there's always water available.
So it's like each molecule has...
Each acid releases its hydrogen ion to a single water molecule, which will then form an H3O plus, and that doesn't now want another H plus because it has a positive charge. And two things with positive charges will do what to each other? Nope. Two things with positive charges. Like charges repel. So that's not going to pick up another H plus.
When you're writing an equation, the boundary equation,
Yeah.
if you had more acids on like the...
I'm going to... Hear me out, Sarah. Kartik wanted to make an easy thing difficult. You want to take something that's already kind of tricky and say, what if we had 7 acids? And I'm going to kindly suggest, why don't we chill out and just hold off on that? You know, we're going to get there. Just like Kartik. Sarah, look at me. I promise I will give you a really hard question where you have to deal with more than one H plus ion. But listen. Shh. How about we get good at this first? Is that fair? Is that fair? One acid at a time. That's what I've always said.
Did you?
Do your acid one at a time. Okay. Anyway. So, in fact, note, there are polyprotic acids, right? But what's polyprotic mean? Poly means protic refers to protons. Polyprotic acids would be like H2SO4, H3PO4, etc. These are acids with more than one hydrogen, acidic hydrogen. They don't lose them all at once. In fact, back to Sarah's point, what she was just talking about, in those cases, you actually have to treat that as being 3 acids in one, each with its own Ka value. So each acid has its own Ka value.
Each acid or like each hydrogen of that acid?
Yeah, again, each of those is actually a distinct acid. The way to think of it is this. H3PO4 is an acid. When it loses a hydrogen, it will now be H2PO4 minus. That is actually also an acid. And then If it loses another hydrogen, it will be HPO4 2 minus. That is also an acid, which can then become PO4 3 minus, which is not an acid. It has no hydrogen to give up. But these get progressively weaker. So this will be the strongest of the lot, and this will be the weakest of the lot. So each one is its own unique acid that has to be considered. But again, Sarah, my plan at this point in the note was to say that's a thing, but we're not going to worry about it yet.
In this unit or?
No, today. We'll worry about this unit. Don't worry. We'll get there. So if you look here, I gave you just some common acids. You can look up a table of 1,000 acids in a textbook, and it will give you all of their Ka values. This is a list of just some of the most common ones. We have acetic acid, also known as vinegar, chlorous acid, formic acid, hydrocyanic, hydrofluoric, hydrogen oxide acid. Water is an acid. Not a very strong one. Yeah. Both. We're going to do a whole lesson on it. Don't worry. We're going to do a whole lesson on it. Lactic acid, nitrous acid, phenol. Now note, there is a note, the larger the Ka value, the stronger the acid. The lower its pHs will tend to be. So if you look at this, on this list, what is the strongest acid? Of these, none of them is a fully strong acid that fully dissociates. These will all be in equilibria. But which one of these is going to be the strongest acid? The most acidic. Sorry? No, that's a negative 10. So is that a big Ka? That's actually a really small Ka. Chlorous acid. Now, if you remember, when we talked about K values, we said if this number was bigger than 1, then it would favor the products, right? And we said if it was less than 1, it would favor the reactants. And if you look here, all of these are less than 1. So when it comes to weak acids, most of the acid, like if you dissolve acetic acid, most of that acetic acid stays CH3OOH, and only a little bit will become the conjugate base CH3COO and release an H3O+. Does that make sense? That's what this is telling you, is that the ratio is going to favor the reactants, the bottom of the fraction, right? Because it's a small number. Does that make sense? So when we're talking about acids, unless you're talking about a strong acid that dissociates all the way, you tend to be talking about things that really don't form very strong acids at all. But we're going to look at an example. We're going to look at formic acid, HCOOH. Here it is. There's formic acid. And formic acid is a pretty boring little acid here. All right, 1.8 times 10 to the negative 4. So we can say about this that it has a Ka value of what? I just said it. 1.8 times 10 to the negative 4. And that equals some fraction. And if we look over here, let's do the reaction. HCOOH is going to react with, what do acids always react with? They need a base, and their base is always water. Very good. And what are we going to get on the other side? This is going to HCOO, and it will now have what charge? Negative. And H3O, which will have what charge? Positive. Good. Okay. So what will the Ka expression for this be? Yeah. Yeah. Yep. But if you remember, do we have to do the concentration of water? No, in fact, we fold it into the constant, right? So there it is. That is our equilibrium expression for formic acid. Now, again, we can ignore water in our ICE table because it doesn't change, right? Concentration of water is so big that using up one water molecule simply doesn't change its concentration. Okay. What does our concentration of acid start out as? Undissociated acid. What's going here? That's the Ka value. What's the concentration we start with? It has to be given to us. You can't just know it. Yeah, in this case, we've made a solution that is 0.025 moles per liter. And before it dissociates, what will the concentration of HCOO be? And what will the concentration of H3O plus be? 0. Okay. There we are. Now, let's do the thing we've always done. Which of these is going down, which is going up? Kardik. No, what's the answer to my question? Uh-huh. So like if I give you a quiz on this tomorrow would be good? Do we want that? Are we feeling smug now again, or are we going to settle down? The question was, what are the signs on these? When we look at the changes, which of these concentrations are increasing and which are decreasing? Very good. This one's going down. What about HCOO minus? It's going up because it's a product. What about H3O plus? Excellent. And one nice thing about acid-base equilibria, every coefficient is always... What are all the coefficients here? Just 1. 1 to 1 to 1. It's always a 1-to-1 stoichiometry, which is nice. It's never going to be 2x, which actually does make the math a little bit nicer, right? So at equilibrium, what will be the concentration here? 0.025 minus x, and here, x and x. All right, we can put that into our equation on the top. 1.8 times 10 to the negative 4 equals, what goes on the top? X times x, and on the bottom? Okay. This is somewhat miserable, team. It's not super miserable, but it's somewhat miserable. What would our next line look like? What should we do? Okay. Okay. Yeah, absolutely. So we could say 1.8 times 10 to the negative 4 equals x squared over 0.025 minus x. What next after that? Thank you. Yeah, we're going to have to move this over to the other side. How do we do that? We multiply it. Okay, so that gets a little ugly then. On the right side here we have x squared. What's 1.8 times 10 to the negative 4 times negative x? Negative 1.8 times 10 to the negative 4 x. Well, that's pretty easy. What's 1.8 times 10 to the negative 4 times 0.025? 4.5. Okay. What does this all have to equal if we're going to do a quadratic? Has to equal 0. I would move everything to the right. Yep. Yeah. No. Let me see it. Yes, that's the one. Sorry. I would move everything to the right. I would set this side as 0, just because we already have that x squared sitting there so beautifully. What's next?
Plus 1.8.
Times 10 to the negative 4, x, and plus minus, thank you, sorry. Excellent. All right. And now we're ready to do what? A quadratic. What does A equal here?
1.
1. What does B equal?
1.8. 10 raised to the
Ugh. Ugly. What does C equal? Almost. Very good. And what will X equal? Well, let's do it. Negative 1.8 times 10 to the negative 4 plus or minus the square root of 1.8 times 10 to the negative 4 squared minus 4 times 1 times negative 4.5 times 10 to the negative 6 all over 2 times 1. Okay. Ooh, she ugly. Right? That is ugly stuff. We got to be good with our calculators here. We good with our calculators? Good. Yeah, these are the numbers I think I got. Is that what you got as well? Amazing. Look at us, team. We should give ourselves a fun team name, like... Not what I was thinking. Gonna be honest with you. I was thinking like... The Eagles. That's boring. We could, of course, check Desmos, make sure we're doing all right. Never a bad idea to check Desmos when you're working on something like this, right? And in this case, we can just say A is equal to 1, B is equal to negative 1.8 times 10 to the negative 4. And what did C equal again? No, B was positive, right? Yeah. And then C was negative 4.5 times 10 to the exponent negative 6. And then we could just say negative b plus the square root of b squared minus 4ac all over 2a. And we could do negative b minus the square root of b squared minus 4ac all over 2a. Now, and I'm going to call this x1. I'm going to call this x2. Because the other thing you can do that is not a bad idea is you can actually plug the original equation in, this one, right? And make sure that you get that. So I'm going to say x equals x1 and x equals x2. Just to show you like how I use Desmos to kind of give me useful solutions, right? Because now I can plug that original equation in, which was what? 1.8 times 10 to the exponent negative 4 equals, what was it on the top? X squared. And on the bottom it was what? 0.025 minus x. And if I've done my job right, that should sit on my solutions. They should be the same, right? Like, you don't even need to name them. You could just do this too. You could also just type those numbers in. I could say, okay, put a line at 0.00203322, blah, blah, blah. I'm just checking my answers, right? I just want to make sure that actually lines up with the equation I had. So if you look here, Those are landing on top of the solutions, which is good, right? And obviously, which of these is the correct solution?
The X2. The negative one. Because we need to get the answer in positive.
But we're doing 0.0. This concentration will be X, and that concentration will be X. So which of these is acceptable? The top one, right? If we use the bottom, we'll end up with a negative concentration. And can you have a negative concentration? Nope, that doesn't mean anything. So this must be the solution, and this cannot be the solution. It's absurd, right? Again, let's be pretentious. Let it never be said that I shied away from pretension. So we can say X is equal to 0.002033. Now, it's easy to forget when you've just done a bunch of very impressive math, and we all did very well, all right, that we haven't actually answered the question, right? Have we answered the question? We have not answered the question. So now we are only in 2 sig fig land. So for our actual answer, what will the concentration of HCOO minus be? 0.0020, right? And what about the concentration of H3O plus? What is it? Yep, very good. And then what about this one? This will be 0.025 minus 0.00203, whatever. So that will be 0.02. So 0.023. Okay. Do you see how little the concentration of an acid actually changes? And this is one of our relatively stronger acids. It has a Ka value of times 10 to the negative 4. Most of the acid stays undissociated. It's a weak acid. Now, the question was what? What was the actual question?
Finding the pH.
What is the pH? Are we ready to do that now? Yeah, because we can do that on the little sidebar here. What does pH equal? pH is equal to the negative log of the concentration of H3O plus at equilibrium, right? It asks for the equilibrium pH. And that's the negative log of what again? Yep.
Didn't it ask us to find it for like formic acid specifically?
Yep.
So put in H3O plus.
The pH of something is the concentration of H3O plus. The formic acid is what is making the H3O plus, right? The definition of pH, the definition of it, it's the power of hydrogen ions. So, look at me. Everyone look at this, just to make sure we're all on the same page, because you're probably going to have the same question, right? You might be tempted to say, oh, that's the concentration of the acid, right? Which in this case is the HCOOH. But that's not the definition of pH. That would be the power of your acid. pH is what's the power on the concentration of hydrogen. And in this case, we call these hydronium ions. You'll hear that term. It's the concentration of hydronium ions. Specifically, it's the negative log of the concentration of hydronium ions. So, what is the concentration of hydronium ions at equilibrium here? Team, are we all looking at me here? What is the concentration of hydronium ions, of H3O plus ions, at equilibrium? 0.0020 molar. And when we take that negative log, that would be 0, that'd be 1, 10, 100. Let's have that 50 around, like, so that would be 2 point, let me guess, 2.7?
2.70.
In my head, team. Even a broken clock's right twice a day. What did we get? 2.7.
2.70.
But we are in how many sig fig land? We are in Yep, but again, what sig fig land are we in?
But it's still 2.698, then it would round to like
We're just rounding the 6 to 7.
69897.
Yeah. Guys, I feel like we're on the same page here. 2.7, right? Okay, good.
This was the answer. So
Okay, 2.
6989.
Okay, that's good. Which
7.
rounds to? Okay, good. We agree. Like we're good. We're friends. We don't have to fight. We can fight. I'm tough. I'm ready. First thing people notice about me. Okay. The pH of what was the original concentration again? 0.025?
Yes.
And this is formic acid, right? So if you make 0.025 molar formic acid solution and let it sit for a few seconds so it comes to equilibrium, it will give you a pH of 2.7. That's its equilibrium spot. And again, that actually means that most of the acid is untapped potential. Of the original 0.025 molar, 0.023 molar of that are still, they've done nothing. Does that make sense? This is what kind of acid? It's not a strong acid, which dissociates all the way, of which there are only a few. The strong acids, if we remember from the beginning, are hydrochloric acid, nitric acid, sulfuric acid, hydrobromic, hydroiodic, perchloric acid, and chloric acid. All the other acids that exist in the universe are weak acids, and they exist in equilibria like this, and so they only partly dissociate. All right, can we see why this is a 2-day lesson? Is that feeling semi-okay? Yeah, we're going to finish this up tomorrow. Is that... Sorry? That's fine. Watch it online. No, I love you guys. I'm a big fan. Big fan. But you're not getting a day off between now and the Friday before Christmas, team. All right? Like, we're going.
Where's your Christmas spirit, Orlando?
Bah humbug. This is my 7-year-old's new thing. He says, "Humbug to you, sir." I say, "Okay, Charlie, that's great." I don't know. So I'll be like, "Charlie, you have to come for dinner." And he's like, "Humbug to you, sir." I'm like, "Sit down at the table." That's how these conversations go. Charlie is 7. It is cute. It's super cute. Can I tell you something awful? Claire was applying to universities and stuff last night, so she's looking at doing something abroad for a year, just looking at different options. So she's going about this, and she's listing all the options, and she's saying, "Oh, I could go here, though." And I look over, and Charlie is just sitting on his chair, listening to her talk about all the places she might be moving, just quietly sobbing to himself. And it was the most heartbreaking thing I'd ever seen in my life. No, she didn't. And then she did, and she looked up, they went and had a big hug, but he was like, "I don't want you to go." Oh, it was horrifying. I'm tearing up thinking about it now. But it was just, well, because she didn't know, right? She was just talking, but oh, it was so sad. Well, yeah, no, we were talking. Like, I was helping her apply. But oh, it was so sad. He was